Section 5.1, Exponential Growth and Decay. So let's start, and let's just say that we have C and K be constants. They could be the same, they could be different, but just the idea right now is that C and K are constants. And then we're going to say that we have some function y is equal to C e to the kt. Then we want to find what is y prime. Well, y prime, that's just going to be chain rule, so that's going to be C times K times e to the kt. Well, this is actually kind of interesting because what happens is this is the solution to a specific differential equation. Now, what in the world is a differential equation? And so a differential equation is an equation where one of the unknown variables is a derivative and then one of the other variables is the function. And so if I have y prime is equal to k times y, I can claim that specifically y equal to c times e to the kt satisfies this differential equation. Notice that if I plug in c times k to the ekt for y prime, which we found y prime to be, and I plug in c times e to the kt in for y, then we will get the exact same thing on both sides. And so this is a solution to this differential equation. Now conversely, if we say that y is equal to f of t satisfies the differential equation y prime equal to ky, then y equals to c times e to the kt for some constant c. Okay. Well, what that means is that the rate of change at a point is proportional at that instant to the original function. And so let's think about this a different way. We know that y prime is the rate of change. Well, if you multiply the function y times a constant k, you're actually getting the rate of change. That is what we're saying. Okay? That rate of change at a point is proportional at that instant to the original function. This is really kind of neat. Well, then we're going to talk about this thing called a growth constant and decay constant, because I claim that specifically this y prime is equal to c times k to the ekt is specifically an equation for exponential growth and decay. And so the growth constant, that is, if k is positive, then the function that we're referring to up here, this y prime is equal to c times k to the ekt, is considered an exponential growth function, and k is the growth constant. Now, if k is negative, then the function is considered to be an exponential decay function, and k is the decay constant. Now, in general, we have an issue, and the issue is that we need a little bit more information to make sure that we can actually find specific solutions to differential equations. That's something that we'll see occurring later on. But right now, what I need to state is that the unique solution of the differential equation with an initial condition, what that's really saying is that if you take that initial function y, plug in some 0, you get a value. And the value we're going to call that thing is p naught or p sub 0. And so p naught or p sub 0 is specifically the constant value of the function when you plug 0 into that function. And so recognize that if you go up to our y above, which is c times e to the kt, you'll see that if you plug in k as 0, you'll just get a constant c. And so since all this is the case, given the fact that y of 0 is equal to this constant I'm telling you is p sub 0, and we know that y prime is equal to k times y, then what ends up happening is that y is then going to be p of t, or our function, our growth function, equal to p naught times e to the kt. Now, a couple things to notate. The reason that P is being used here is because often we're talking about populations, and so really P of T being growth constant or decay constant is the population of something. And so specifically this setup just allows us to find that P sub naught. So let's actually deal with an example problem. So let's say that we're told that after T hours, there are P of T cells present in a culture, where specifically we're told that P of T is equal to 5,000 times e to the 0.2 t. Now, this is specifically one of these growth or decay functions, but let's actually address what it is. Well, notice that if you look at k, k is 0.2, it's positive. And if k is positive, then that means that we have a growth function, not a decay function. And so this is actually going to be an exponential growth function. Alright, so then let's ask some questions about this specific function. Let's ask how many cells were present initially. That is, what was the initial population of the cell culture? Well, I claim that P naught is that answer, but how can you do that? Well, if you know that T is time, and you say, well, what is P of 0? P of 0 is then going to be 5,000 times e to the 0.2 times 0, which e to the 0 is just 1, so that's just going to be 5,000. So initially there were 5,000 cells in that culture. Well, we plugged in P of 0, and so this is our P sub 0, or our P naught. So now what we want to do is we want to give a differential equation satisfied by P of T. Now, don't get too stressed out about this. Remember that really we know what this is, right? Specifically, that equation is going to be our function prime is equal to k times the function. And so I'm going to write that in terms of my function P of T, and so that's going to be my function prime is equal to my constant k, but remember that k here was 0.2, so that's going to be 0.2 times my initial function P of T. And so that's actually the differential equation satisfied by the function that we're looking at. Okay, so now we have a question. When will the initial number of cells double? Alright, well, if the initial number of cells was 5,000, what that means is that now we just set our equation that we were given, P of T, equal to twice that, so that's going to be 10,000. So, let's do that. That's going to be 10,000 is equal to 5,000 times e to the 0.2 t. Okay, so then I can divide by 5,000, divide by 5,000. I then get that 2 is equal to e to the 0.2 times t. So if we're trying to solve an exponential function, what can we do? We can take the natural log of both sides. That's then going to be natural log of 2 is equal to 0.2 times t. And so then I can divide by 0.2, divide by 0.2, and I get that t is equal to the natural log of 2 divided by 0.2. At this point, if we want to find an approximation, let's do that. And if I round to one decimal place, this is approximately 3.5, and so we're finding time. That's specifically in hours. Okay? Well, then we want to know when will 20,000 cells be present, but we would take the exact same approach. Set that function equal to 20,000. So 20,000 cells equal to 5,000 e to the 0.2 t, divide by 5,000, divide by 5,000. I get 4 is equal to e to the 0.2 t. I can take the natural log of both sides, and so I get that the natural log of 4 is equal to 0.2 times t. Divide by 0.2, divide by 0.2. I get that t is equal to the natural log of 4 divided by 0.2, which is approximately 6.9 hours. Well, now we want to know at what rate will the population of cells be increasing when there are specifically 100,000 cells. This is actually one of the main reasons to use that differential equation stuff right now. And that is, we know that p prime of t is equal to 0.2 times the population at some time t. Well, what are we trying to find? We're trying to find at what rate will the population of cells be increasing when there are 100,000 cells. This is specifically the population at some unknown time t, and so that tells me that p prime of t is equal to 0.2 times 100,000, which is exactly 20,000 cells per hour. And so it's 20,000 cells at that moment in time. We looked at a growth function, so now let's look at a decay function. Radioactive cobalt-60 has a half-life of 5.3 years, and we want to find its decay constant. And so the first thing to note is that you can use the P of t for population like we did earlier, but now that we're talking about radioactive decay or a substance, maybe you want to talk about an amount instead of a population, and so you could use a function variable of a of t where it's the amount given some amount time. And so based on that initial value stuff, we don't actually know what it is, but we're trying to figure out what the initial amount is. And so I claim that that initial amount is a sub 0, or a sub naught, a naught, times e to the kt. I want to solve for k if possible. Now specifically there's something to consider, and that is, if we know half-life, what in the world does that mean? Two things. First off, because it's decay, we know that our k value will be a negative value. That's just an error check. But we know that at 5.3 years, a of 5.3, we're going to have literally half of the amount of stuff we started with. And since we're going to have half of what we started with, that's the amount left over, which is then going to be equal to a sub 0 times e to the k times t 5.3. And so now we have an equation that we can solve for to find k. At 5.3 years, we have half the stuff that we started with. Well, if we have half the stuff that we started with, what can we do? We can assume that for the moment, a sub naught is equal to 1. And then if a sub naught is equal to 1, then that's going to be 1 times e to the k times t, where t is 5.3. And so now we just need to solve for k. Well, if I have 1/2 is equal to e to the k times 5.3, I can take the natural log of both sides. That's going to give me the natural log of 1/2 is equal to the natural log of e times k to the 5.3. We're just going to be left with 5.3 times k. And so now I can divide by 5.3, divide by 5.3. That's then going to give me that k is equal to the natural log of 1/2 divided by 5.3. And if we want an approximation, I get that my decay constant is approximately negative 0.13. Pay attention to the decimal rounding. The rate at which the number of cells changes is proportional to how many cells are present. In 6 hours, a population of 1 million cells grows to 9 million. How many cells will be present 15 hours after the population was 1 million? Alright, so to make our life easy, they give us 1 million, 9 million. We're going to just use 1 and 9, and we're going to assume our units are in terms of millions. And so if that's the case, our initial value is going to be 1, where our units are millions, like I said. Then we're told that in 6 hours, a population of 1 million cells grew to 9 million. So what that means is that we really can just assume that since our initial is 1, our population function is going to be equal to 1 times e raised to the kt. And so p of 6 is going to equal 9, which is of course then going to equal e to the k times 6. And so now I can solve for k, take the natural log of both sides. That's going to be the natural log of 9 is equal to natural log here, 6k, divide by 6, divide by 6. We get that k is equal to the natural log of 9 divided by 6. Now, because we're dealing something with these units of millions, I want to be really careful because the error could show up pretty bad. And so I'm going to use the exact value for the constant k, which is the natural log of 9 over 6. And so specifically that means that my population function p of t is equal to e to the natural log of 9 divided by 6 times t. And so we don't get messed up, I'm going to put the t out front. So it's t times the natural log of 9 divided by 6. Now at this point, we just want to figure out how many cells will be present 15 hours after that. Well, 15 hours after that is going to be p of 15, so that's going to be equal to e to the 15 times the natural log of 9 divided by 6, which I get to be 243. Remember that our units are million, and so that's 243 million cells after 15 hours.